Hello, students, and welcome to this lecture on properties of real fluids. Now, here you will try and understand how do we represent and how do we study the properties of real fluids. Now, what are real fluids? Real fluids are fluids by definition are gases and liquids. You see, fluid state is a state where it can be either a gas or a liquid. Both are fluid. What does fluid mean? Fluid means any substance which is whenever it is applied pressure, it flows. Both gas and liquid, whenever any pressure is applied on them, they will start flowing. Therefore, we call gases and liquids as fluids. Now we will study their properties in this lecture. Now let's do a very small thought experiment. What we can do is we can take a vessel and bath put it in a bath where the bath can be used to heat up the vessel, and we put liquid in this, and we constantly monitor its temperature. Okay, and we maintain the pressure. We maintain the pressure, so the pressure is maintained. What we do is we start increasing the temperature. Initially the temperature is at T1, but the pressure is held constant. As we increase the temperature, there comes a temperature when the first bubble of vapor is seen in the fluid. This is the start of boiling, and this state is known as the saturated liquid state. If you further heat it, the liquid is now going to get converted into vapors. When all the liquid is converted into vapors, we call it saturated vapors. And when we further heat the vapors, they are called superheated vapors. Now, point A in this diagram, which is in the left, is a supercooled liquid. It's a liquid which does not have any vapor. When you start heating it, it reaches point B, which is nothing but the saturated liquid state. When you further heat it and all the liquid gets converted into vapor, we get the saturated vapor. And when we further heat, which is point C, and when we further heat those vapors, they become superheated, which is represented by point D. What we should note for the liquid is A is known as a subcooled liquid, or all liquids are known as subcooled liquids. Next, pay attention on the two-phase region. Now, what exactly is this two-phase region? When we start heating the liquid and it comes to the saturated liquid state, a specific amount of heat is required to convert the entire liquid to vapors. This is known as the latent heat. As we give parts of latent heat, parts of the fluid starts vaporizing off. What I mean by that is, if we give half of the latent heat, then only 50% of the fluid will get vaporized off. If I give 25% of the latent heat, only 25% of the latent fluid will get vaporized off. So therefore, this two-phase region represents the partial transfer of latent heat. Okay, if we partially transfer the latent heat, the mixture will be a mixture of vapors and that of liquid, and therefore it's two-phase, and we call this region as two-phase region. When we give the complete amount of latent heat, it gets converted into saturated vapor, and when we further give heat, it is superheated vapor. Now the temperature at the start of boiling is Tsat, and the temperature also at the end of boiling is Tsat. As we can observe, if the pressure is held constant, the boiling point, that is Tsat, it is constant. This applies to all liquids without exception. If we hold the pressure constant, the boiling point is constant. Now let's look at another diagram, and let's do a thought experiment. What we do here is, we take liquid, we maintain it in a water bath to start with. We note its temperature and we make an arrangement to depressurize it. So this is a vacuum pump. This is a vacuum pump. Now what this vacuum pump will do is, it will reduce the pressure on the liquid, and we have an arrangement to note the pressure also. To start with, at A, let the temperature of the liquid be T and its pressure be P. When we start reducing the pressure on it, its volume is going to increase. But as you can see that AB is a straight line and it is almost vertical. What does this mean? On the PV diagram, this means that as you reduce the pressure on the liquid, its volume does not increase much, or rather, its volume tends to remain almost the same. I'm not saying it's the same, but almost the same. So, one engineering takeaway you can have is, as you change the pressure on the liquid, its volume hardly changes. Further, if we reduce the pressure and come to point B, we suddenly find the first droplets of vapors in the liquid. Now, this is known as the saturated liquid condition. And the pressure at which this happens for temperature T, mind you, in all this operation, the temperature has been held constant by using the water bath. This is your water bath. The temperature has been held constant using the water bath. Now, as we reduce the pressure and we find the first droplets of vapor coming, the pressure at which this happens, which is point B, is known as PSAT or the saturation vapor pressure. Now note, if we further reduce the pressure very slightly, a slight amount of increase in pressure is given, all the liquid will convert itself into vapor. You can say for practically that at PSAT, all the liquid converts itself into vapor and comes to point C. When all the liquid has converted itself into vapors, we call it saturated vapors. Further, if you reduce the pressure, the volume follows the gas law. This is point C to D. Okay, this is point C to D. It further follows the gas law. So, this region, the region to the right of the saturated vapor line, is known as the superheated vapor region. And the region to the left of the liquid line is known as the subcooled liquid region. Now, let's take all this, what we have learned, and learn the entire pressure volume diagram for the liquids. The pressure volume diagram for real fluids is on your screen now. As you can see, you have a saturated liquid line at the left end, you have a saturated vapor line at the right end, and they both meet at the critical point. At critical point, there is no change in volume when it goes from liquid to vapor state. This is the definition of a critical point. At critical point, at and above critical point, there is no phase change as you increase the volume or decrease the pressure. If you take a critical fluid and you reduce the pressure on it, there are no sudden volume changes. But when you take a subcooled liquid and you reduce the pressure on it, there is a sudden volume change during boiling. The liquid to vapor volume ratio would be 1 is to 1000 or 1 is to 700. Okay. Now, as discussed earlier, small letter A, B, C, D. This is an isotherm. What is an isotherm? Isotherm is constant temperature line. If a liquid at A is taken and it is depressurized, it will follow the line A, B, C, and D. If a liquid is taken and heated at constant pressure, it would follow the line capital A, B, C, and D. This is known as an isobar. In between the saturated liquid line and the saturated vapor line lies the two-phase region where the mixture is liquid plus vapors. What you see, the blue dotted line is the constant quality line. This constant quality line, on this constant quality line, any point represents a fixed percentage of vapor in the liquid. How we define quality as? We define quality as X, which is going to be equal to mass of the vapor in a mixture of mass of liquid plus mass of vapor. So if we take a mixture which has both vapor and liquid, its mass is going to be ml plus mv. The ratio of mv upon ml plus mv is known as the quality. Now the quality line or the constant quality line represents constant X in the two-phase mixture. It's obvious fact that the quality, if it is X is equal to 0, it means the entire mixture contains only liquid. And if it is X is equal to 1, the entire mixture contains only vapors. If it is X is equal to 0.5, 50% by mass of the mixture contains vapors. So this is a very good way when steam is supplied. This is a very good way of knowing what is the steam, whether the steam actually contains liquid droplets, or the steam is completely superheated vapors. To know the energy of steam and to do calculations on it, we usually use the pH diagram. That is the pressure versus enthalpy diagram. It's on your screen now. Let's study it. I have taken a portion of this pH diagram and plotted it here. Now, what is the meaning and how a pH diagram is plotted? We'll discuss this. Let us say we have a liquid at A. Now, this is a subcooled liquid. If we heat it up at constant pressure, its change in enthalpy is going to be specific heat of the liquid, that is Cp liquid, multiplied by T minus Ta. Now, when it goes from A to B, where B is nothing but the saturated liquid state, the change in enthalpy is going to be Cp liquid into T sat minus Ta. If you further heat it up from B to C, as discussed earlier, and once again reminded to you, the amount of heat that would be required would be equal to the latent heat. Delta HBC is nothing but lambda. That is the latent heat required for vaporization from saturated liquid state to saturated vapor state. Now, if we further heat it up from C to D, it would be a superheated vapor. At D, it would be a superheated vapor. The amount of enthalpy required to get it from C to D would be delta H CD is equal to Cp vapor into Td minus Tsat. Reminded to do you once again, and as is obvious from this diagram, when it goes from B to C, the pressure is constant and so is the temperature. It is because when it is going from B to C, it is boiling. Boiling for pure fluids is a constant pressure and constant temperature phenomenon. By this, what I mean is, if you hold the pressure constant, there is only one unique boiling point that the fluid is going to happen. Now I'll come to the subject of boiling. What we colloquially talk about boiling as, and what is boiling in engineering. Let's take a vessel and let's take liquid in this. Now this liquid is kept in the atmospheric condition. It is kept in the atmosphere, open. Now we start giving heat to it and boiling it. Q. We note its temperature. Now let's plot time versus temperature. What you will find is that as the time goes, the temperature increases. This is not boiling. In chemical engineering, this is known as heating. We usually refer to this as boiling colloquially in the sense that that is the sense we have, but it is not. It is heating. We call it heating. Now, when it comes to the saturated temperature or the boiling temperature, whatever heat you give to it no longer is used to increase the temperature but is used to vaporize the fluid. So the temperature remains constant during boiling. The temperature remains constant during boiling. Once again, as you further, when everything has been vaporized off, now at this point, everything has been vaporized off. You further heat it up, the vapors are superheated. This particular region is known as boiling. This is known as superheating. This is known as superheating. So you only superheat vapors. You heat liquids and you boil liquids. To liquids, you heat them. When you heat them, its temperature is going up. When no longer the temperature is going up, whatever heat you are supplying is only being used to produce vapors or make vapors. You call it boiling. If you have the vapors post boiling and you are further heating it up, this is known as superheating of the vapors. So one should be clear on these concepts of what is boiling. Now, as you must have studied in your previous classes, and it's being reminded once again that boiling point, when we refer to the boiling point, we refer to the boiling temperature. Now, the boiling temperature is a function of pressure for real fluids. Now, let's have a look at this diagram. A few things should be obvious from this diagram. One is, as we go up in the left, that is, as we increase the pressure, the boiling point increases. That is, this line AB, line BC, and line capital B and capital C, as we increase the pressure, it goes up. As it goes up, the isotherm passing to it has a higher value. What I'm trying to say is, as you increase the pressure, the boiling point goes up. But the boiling point is fixed. If you fix the pressure, the boiling point is fixed. As you reduce the pressure, the boiling point reduces. What is important to note from this diagram also is that as you increase the pressure, the change in volume from saturated liquid to saturated vapor reduces. But as you reduce the pressure, the change in volume from saturated liquid to saturated vapor increases. Now, this is a very important phenomenon to note. All engineers, chemical engineers, should actually be having a very clear view of this, that as you change the phase by boiling at a higher pressure, the change in volume reduces from liquid to vapor. But as you do it at a lower pressure, boiling at a lower pressure, the volume changes are high. Something similar happens if you look at the pH diagram. The top red star in the pH diagram is nothing but the critical point. When you boil any fluid at a lower temperature, let us say 40 degrees Celsius, as you can see, the enthalpy of vaporization is high as compared to the enthalpy of vaporization required when it is at 200 degrees Celsius. So it is very clear that if you boil at reduced pressures, the enthalpy for vaporization is high. But if you boil at increased pressures, the enthalpy required for vaporization reduces. And it's an obvious fact that at critical point and over and above it, there is no enthalpy of vaporization. Therefore, above critical point, you cannot have a concept of boiling because there is no phase change which occurs. So I hope I have clarified a lot of things on the properties of real fluids. Have a great day.